All right, so for the next step of the problem, we're going to go through and find the p matrices that we need to go and use the putzer algorithm. And again, P0 is always the freebie. It's always the identity matrix. But this time around, it is the 3x3 identity matrix. So it's 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now P1, that's always found by taking the matrix A, which in this case is -1, 0, 0, -1, 1, -1, -2, 4, -3, and subtracting -1 times the identity matrix, which again, of course, is 3x3 for this problem. Okay, the net result of that, of course, is adding 1 to the main diagonal. So P1 is going to have our top row being all zeros, and then our second row is going to be -1, 2, and -1. Then the third row is -2, 4, and -2. Now for the third matrix, P2, that's going to be the A minus lambda 1I, which is above. That's our 0, 0, 0, -1, 2, -1, -2, 4, -2. And that's multiplied by A minus lambda 2I, which just coincidentally ends up being the same matrix because lambda 1 and lambda 2 are exactly the same. So that's just that matrix times itself. And at this point in the problem, it's probably a good idea to get a graphing calculator out and multiply these matrices out with the calculator instead of doing this by hand. But if you do multiply it out on your calculator, you end up with the zero matrix, which is again just a 3x3 matrix full of zeros in this case. So if you now think about the putzer algorithm, there's no need for us to go through and find the R3 function because the P2 matrix is equal to 0. And therefore, this last term here is going to be 0 regardless of what the value of R3 is. So at this point, we can kind of stop and take note that we have our 3 P's. Next, we'll find our 3 different R's.